see the screen. Now, okay, the first thing is that, I mean, you have already studied, I think, you have already studied the pumping lemma. Haven't you studied? I suppose you have already studied the pumping lemma, right?
Yes, sir.
Yeah. So I
Yes,
think
sir.
that first thing which is written there, computing 2 to the power p times 2 to the power p for an arbitrary value of p, that you cannot do using finite state machines. So, or for that matter, finite state transducers. So, I think I can leave this as an exercise to you, although it is as such explained there. But you can do it on your own because you have already studied this topic. So let us move over to the notion of state equivalence. So as you can see, we consider two types of machines, finite state machines, machines that are and machines that are as we shall see, it's easier to minimize in the first case. This is all right. So let us just, so distinguishable states, okay. So, you can have a machine. So it's a finite state machine. It's a finite state machine. So let us say that you have two copies of the machine, and say this machine is in state I and this machine is in state J. All right. So you apply the same set of inputs. You apply the same inputs. Or you can say sequence of inputs. So this machine is in state I, this machine, and then you observe their output. Okay. You observe their outputs. Now, if the outputs are always the same, then you really can't distinguish between these two states. of these two states Si and Sj. And if there is a sequence of inputs which gives you different outputs, then you could say that using that sequence of inputs, you can distinguish between these two states, Si and Sj. All right. So that is the idea of distinguishable states, and the sequence which allows you to distinguish between these two states is a distinguishing sequence for that pair of states.
ओ भाई ये तो दूसरी जगह चालू हो गई, लोग उसमें ज्वाइन करके बैठे हुए हैं, पता नहीं कहाँ था।
All right. So you have, so that's how you can. So two states can be, if two states are distinguishable, then there's a way to distinguish them. Now, if you can distinguish them with a sequence of length k, then those you can say that those are k distinguishable. Okay, there exists a sequence of length k to distinguish between these two states, then you could say that those are k distinguishable. And so, by that token, they can be said to be k equivalent if there is no sequence, if there is no sequence of length k to distinguish between Si and Sj. All right. And of course, two states are equivalent if they're k equivalent for all k, all right, for all k. But since these are finite state machines, you need not make k too large, okay? So if there's an n state machine, so it's enough to check sequences of length up to n minus 1. All right. I mean, so let us just see how we can employ that principle here. All right. So if you look at this machine on the left, one thing is quite evident, that all the states have an output of 0. It's a Mealy machine, and all the states have an output of 0 when the input is 0. All right. So okay. So now so you have sets A, B, C, D, E, and F. So this is what we are calling the initial partition. So you do not know. So to start with, you assume that all the states could be equivalent. So now we look for one distinguishable sequences. So that means, can we give a sequence of length 1 to distinguish? So in fact, the answer is yes, because as you can see on the, for x equal to 1, you can see that some state, or all states do not have the same output. So let us see. So you can see that B, D, and F. B, D, and F, they have output 1. Maybe I'll just put it on the other side. B, D, and F have output 1. Okay, so let me just say that, these have output 1. And the remaining ones, oh, sorry, just wait. Let me, I might have made a mistake. Let us look at the output 0 first. See, B has an output 0. B, D, well, B, D, and F actually. B, D, and F have output 0. Okay. B has output 0 when you give input 1. D has output 0 when you give input 1. So it is still B, D, and F. So these have output 0 when you have, so on input 1 the output is 0, all right, and the remaining ones, say A, C, and E. A, C, and E, on input 1 these have output 0, output 1. Okay, so you can distinguish between between these states. So B, D, and F, if the machine is in either, if the initial state is either B, D, and F, then you can distinguish those states from these states, A, C, and E, all right, giving an input of 1. Is this okay? Now, let us see what happens when you have, when you go over to the, let us see what happens. So now, suppose you are in, so let us look at B, D, and F. So B goes to, so let us say B is 1. Let us say D also goes to F and B. And so look at the successors of B. Okay, B goes to either F or D, which are in the same partition. Okay. So on input 0 it goes to F, on input 1 it goes to D. So both of them are in the same partition. Look at D. D also goes to F and B. Both of them are in the same partition. All right. But if you look at F goes to B on x equal to 0, C on x equal to 1. All right. So you can distinguish F from B and D. Just a minute. Yeah. I mean,
Sir, you are muted, sir.
CRM, can you please unmute yourself?
Okay. So yeah. So suppose let us say that the machine is initially in B, and let us say that the machine is initially in F. So now suppose you give a 1, all right? So on 1, this one goes to C. Of course, the output is output is 0, right? From B, yeah. So it is, and it goes to D, and F on a 1, it goes to C. Well, if you still get a 0, but it goes to C. Now, I've already seen that D and C are distinguishable, so you make use of that. So on 1, so D goes to B. Yeah, so this goes to B, giving a 0. And this one, C, goes to B, giving a 1. All right, so now giving a 1. So as you can see, it is distinguishable now, right? This one gives a 0. So this is, so the fact that, so now you are utilizing this result recursively. So the fact that, so if these make a transition to states in different partitions, then because D and F are not one distinguishable, but as you can see, these are two distinguishable because they make transitions to, they have successors in different partitions which are distinguishable. All right, so you are able to split this as follows. So BDF can be split to BD and F. All right, now let us look at A, C, and E. So A, A makes a transition to E. A, C, and E. All right. So A makes on 0, A goes to E, and C goes to E, and E goes to C. So on 0, on 0, they go to the same partition, right? A, C, and E have transitions to C and E only. So that's all right. But what about 1? On 1, A goes to D, A goes to D, C goes to B, and E goes to F. So these are distinguishable because B and D are not too distinguishable, but but F, B, and F, D both are too distinguishable. So what we saw was E. E goes to F. All right. So E goes to F, whereas A and C are not. These are not three distinguishable. All right. So A and C both go to D and B, or B and D, which are in the same partition, and but E has a transition to F, which is in a different partition to B and D. So now these are therefore distinguishable, three distinguishable. So let us check further if we can. So what about B and D? B and D, B goes to F, D goes to F, and so B and D are You can't distinguish between B and D as yet. B and D, yeah. So BD so far remains the same. F, of course, it is singleton. Let us see whether anything happens to. So this is D and B. So it looks like A and C. So A and C, D and B. So so it looks like we cannot distinguish between these either. So this seems to be so now we have reached a fixed point. So I think yeah. So B and D. Yeah. So yeah. So now these are the equivalence partitions. So if you go further, you will stay with the same partitions. All right. So you have reached a fixed point. So these are the equivalent partitions. So now, so therefore B and D are indistinguishable. A and C are indistinguishable. All right. A and C are indistinguishable. So you can, so you could, just drop them. So you have BD and AC are equivalent. So now you can reduce this machine. Okay. So what you saw is, let us just copy this. So these are the equivalence partitions. So A, B, you don't want C, you don't want D, so E and F. So this is well, just move it down. So you have x equal to 0. X equal to 1, and you could write this as E0, well, B1, this is F0, B0, this is E. E is A0, F1, and F is B0 and A. So this is your reduced machine. You have got 4 states, A, B, E, and F. And so the minimization of completely specified machines is quite easy. All right. It's quite easy. So yeah. Okay. So let us, yeah.
Sir, can you explain these partitions means exactly what does P0, P1 mean? Like
P0 is the initial uncertainty. So you start off, you start off with assuming, you start off with the assumption that all these states may be equivalent. All right. This is your initial uncertainty. You don't know really which of these. So you start off assuming that all of them are equivalent. And then you test your assumption. So first of all, what we are doing is in P1, where so using giving one input. So these are so these two partitions, BDNF and ACNE, these are one distinguishable, as you have seen. So if you give a 1, if your machine is in either BD or F, if you give a 1, you get an output 0. And if your machine is either in AC or E, if you give a 1, you get an output of 1. So these two set of states are one distinguishable. All right. Next, what you can see is that well, actually in this step I have taken a little bit of a shortcut. When I split AC and E, I made use of this. If you look at, I made use of this partition. I need not have done that. So if I had just looked at these partitions, AC and E, so let me do it in a different color. So AC and E, if you look at AC and E, so on input 1, this goes to DB and E goes to F. Now F is I made use of this, but if I look at this, then actually so let me just redo it a little differently. That's all. I'll still get this, but so let me just yeah, so B and F we had got, that is fine. B and F we had, but if you look at, if you look at if you look at P1, then AC and E are not immediately distinguishable. But at this stage, they become distinguishable. So if I only look at the previous partitions, at this stage, AC and E are not distinguishable. If I look at these partitions, so then of course I get P4 equal to this. All right. So yeah.
Yes, sir.
Okay. So this is how you can minimize this. So this is completely specified. So completely specified means if the machine is completely specified, means for okay, so that is what you mean by a completely specified machine, if you like. Completely specified sequential machine. All right. So that's a completely specified sequential machine. Now, if the machine is not completely specified, means either the next state is not defined or the output is not defined. So then it becomes an incompletely specified machine. So machines may be incompletely specified also. So you have here some examples of incompletely specified machines. So let us just look at some examples. So say if you take MA, in case of MA, as you can see, some outputs are not defined, okay, but all the next state transitions are defined. If you look at MB, you find that sometimes the next state is not defined and sometimes nothing is defined, neither the next state nor the output are defined. So these are, various examples of incompletely specified sequential machines. All right. So in this case, only some out. In case of MC, only some outputs are not defined. So these are various, these are there. We can use these machines as examples. All right. So let us look at some basic notions for. So for a completely specified machines, so far we have considered equivalence. Now, for incompletely specified machines, we'll consider the notion of compatibility. So this notion of compatibility is also, we don't normally need the notion of compatibility, but for completely specified machines, but that notion can be, is also applicable to completely specified machines. So first, let us just talk about compatibility of two states of a completely specified machine. So for a completely specified machine, two states Si and Sj are compatible if and only if for every input sequence, the same output sequence will be produced regardless of whether Si or Sj is in the initial state. So that we have seen. Now, for an incompletely specified machine, you have some issues which you don't have for completely specified machines. So the first issue is that the next state itself may not be defined. So you have already seen, you can see here also. So for some of these, in some cases, the next state itself is not defined. So we have a new concept here. There's an applicable sequence. So you say that an input sequence is applicable to a sequential machine if for that sequence the state transitions are all defined. Okay. So if the state transitions are defined for each input of a sequence, then that sequence is said to be applicable to that machine. Of course, one thing that is missing is um, whether you want to. Well, I mean, the way it is given, this. Well, we are more interested in whether the input sequence is applicable when the machine is in a certain state. Okay, so I think that part is missing from that. So an input sequence is applicable to a machine when it is in a certain state. If it is in, say, state Si, then starting from Si, all the transitions should be defined for that sequence. All right. So that is the notion of an applicable sequence. So behavior of machines may be observed when So you can do a similar experiment as we did earlier. That is shown in this diagram. That is shown in this diagram. So maybe I can just move it a little down. Yeah. So you could so here for sequential machines, there will be a new thing. That is, this sequence will be applicable. Will be just to it will be an applicable sequence. So because if you do the experiment with a sequence that is not applicable to both Si and Sj, then you can't really do that experiment properly, because at some point the state transition, the next state is not defined for one of the machines maybe. So you do the experiment with applicable sequences and observe the outputs. So because the next state transitions are defined, then you can therefore you can do the experiment. And what is the compatibility issue? So here you want the you can say that well, let us just say here outputs should match when both are defined. Okay, so that is the requirement for compatibility. And Sj. All right, so this is the requirement for the compatibility of Si and Sj. So these are the two important things. Should match, or maybe I can just put in a different color. So they should match when both are defined. And those are for applicable. So for each applicable sequence of, this is, we can say, for each applicable input sequence, output should match when both are defined. All right. So that is the notion of compatibility of states. Now, why we are interested in this notion of compatibility? Because, uh, because certain things are, I mean, you could have, let us say, SI, SJ, and SK. So SI and SJ may not, be compatible, but it is possible that SI and SK are compatible and SK and SJ are compatible. So this sort of a situation is possible in case of an incompletely specified machine. All right, in case of an incompletely specified machine, maybe I'll just put it this way. So these may not be compatible, but SI and SJ may not be compatible, but it is possible that SK and SI are compatible and SK and SJ are compatible. So this compatibility, as you can see, is a richer notion than equivalence. All right, it's a richer notion than equivalence. All right, I think we can stop here today. We'll continue in the next class. Yeah, someone is saying something?
Yes, sir. I had a doubt. While checking the compatibility of SI and SJ, like the start state will be SI and SJ themselves or something else? Like
Yeah. Starting with SI and SJ, that was shown in the diagram, in fact. It is, one is starting with SI, the other is starting with SJ.
okay, sir.
Yeah. All right.
Sir, if we transition from a state such that the next state is not defined, then what will happen?
Then that sequence is not applicable. Because
No, sir, that is okay, but what will the machine do?
it can be in any arbitrary state. It is not defined. See, that means you don't care really. I mean, see, I'll just give you an example. Say, for some input, you reach a state which indicates that means something is means you cannot proceed. Okay, you cannot proceed. So after that, it doesn't matter what input you give next. I'm just giving an example. Say you come to the gate and present. So two persons, say person I and person J. So let us say person I comes with a valid identity card and person J comes with an invalid identity card. So now, if you come with a valid identity card, so you say that, okay, the card has been recognized. So you go to a state where the card has been recognized as a valid identity card. And say for person J, you say that, okay, this card is not recognized as a valid identity card. Now, for person I mean, who has come with a valid identity card, there are maybe some other things. I mean, maybe suppose you come for convocation, so you have a number of other things to do. But person J who has not come with a valid identity card, for him those steps are no longer applicable, right? So it is like that. So basically, you have reached a state after which the next state is not defined. So you just basically there is no point in defining subsequent states. Okay.
Okay, sir. So when we make a machine physically and then we put in such an input, then will it continue producing arbitrary outputs or will it stop?
Yeah, so I mean that is up to you to decide how you are making the machine. So, I mean now this is a more abstract notion. That means you're not defining that state. So basically, you will not consider the you will not consider the compatibility of those two states. Will not really consider the compatibility of those two states because this sequence is not applicable to you have input sequences which are not applicable to those. So yeah, you could I mean in practice you might take the machine to a dead state or something like that. Yeah. Okay.
Okay, sir.
So we'll see. We'll see how these are handled in subsequent examples. Okay, then let us stop now, I think. Yeah.